Okay, so the next question asks us to use the comparison test to determine which one of the following series is divergent. Okay, so before we do anything, the first thing we should concern ourselves with is I'm asked to use the comparison test in these series, but when can I use the comparison test? I can only use the comparison test when all the terms in the series are positive. But we can see for all of our cases, they're all going to be positive. Okay, so we'll carry on with the first question. So we have this sum n equals 1 to infinity of 1 over n to the 3 halves plus 1. And whenever you want to use a comparison test, you have to think to yourself, like the problem with the comparison test is to figure out what to compare it to. Okay? So you need to ask yourself what determines the behavior of this series. Okay? So in our case, again, we have n equals 1 to infinity, n to the 3 over 2 plus 1 over 1. Okay? The guy that's going to determine the behavior as n goes to infinity is this 1 over n to the 3 over 2. Okay? That's going to determine how this decays. So our instinct should be to compare this to 1 over n to the 3 over 2. Now, can we do that? Well, we know that n to the 3 over 2 plus 1 is greater than n to the 3 over 2, just because we're adding 1 to one side. So if we flip this, 3 over 2 plus 1, it has to be less than 1 over n to the 3 over 2. Okay? So we have our criteria for using our comparison test. We have positive terms where an is less than bn. Okay? And what do I know? Well, I know by the p test that n to the 3 over 2 inverted sum is convergent by the p test. Because in our case p equals 3 over 2 is greater than 1. Okay? Therefore, by the direct comparison test, we must get that n equals 1 to infinity, n to the 3 over 2 plus 1 over 1 converges. Okay, so b is very similar. Okay, you've got this quotient 1 over n squared plus 8. And our instinct again should be the n squared is going to determine the behavior. So we're going to look at n squared plus 8 is greater than n squared. So if we flip, n squared plus 8 is less than 1 over n squared. So if I can show the series where this is the an converges, then by the direct comparison test I'm going to get that the series we want converges. And 1 over n squared, n equals 1 to infinity, converges just by the p test. Therefore, or that implies that our series converges by the direct comparison test. Okay, so with the next problem, we're looking at the sum n equals 1 to infinity of n squared minus 1 over n cubed plus 100. Okay, so this is a case where we have a quotient of polynomials. So we want to compare that to bn, where we have n to the highest power in the top. Now the highest power that appears in the top is n squared, so the highest power is 2, and the highest power that appears in the denominator is 3. Okay, so this is 1 over n. Now, we want to use a limit comparison test with this. So lim n goes to infinity, an over bn. In our case, lim n goes to infinity, n squared minus 1 over n cubed plus 100 divided by 1 over n, which is just multiplied by n over 1. Okay, so this is equal to lim n goes to infinity of n cubed minus n over n cubed plus 100. So if we want to see what this limit is, we can divide top and bottom by the highest power of n, which is n cubed. So lim n goes to infinity, n cubed divided by n cubed is 1, minus n divided by n cubed is 1 over n squared, all over n cubed divided by n cubed is 1, plus 100 divided by n cubed. So in the limit, this guy is going to stay at 1, this guy is going to go to 0, stay at 1, go to 0. So we end up with 1 minus 0 over 1 plus 0, which is just equal to 1. Now, the limit comparison test then tells us that if we look at these two, n equals 1 to infinity, n squared minus 1 over n cubed plus 100, and sum n equals 1 to infinity of 1 over n, because we've got this finite positive number greater than 0, we have that either both of these converge or both of these diverge. But by the p-test, we know that this diverges. So diverges by p-test. Okay? So we have now that this diverges by the limit comparison test. Okay, so for the next problem, we're looking at the sum n equals 1 to infinity of 7 times 5 over 6 to the n. Okay? So we can clearly see that this is a geometric series where our multiplier, so r, is 5 over 6, which is less than 1. So we know this is going to converge, and we can actually find exactly what it converges to. That might be a useful exercise. I think it converges to 35. Okay? But we're asked to use a comparison test, so let's just do that. Okay? You have to ask yourself again, what do I want to compare it to? Well, the answer to that you'll find if you think about what dictates the behavior. In this case, the 7 isn't going to dictate the behavior. It's the 5 over 6 to the n. So let's just compare it to that. So bn is 5 over 6 to the n. Okay? But our bn isn't going to be bigger than our an because there's a 7 in front of our an. So let's just use the limit comparison test. Lim n goes to infinity. An over bn, in our case, is going to be 7 5, 6 to the n over 5 over 6 to the n, which is just lim n goes to infinity of 7, which is just 7. Okay? So we've got a positive constant. So we know that this series converges if this guy converges and diverges. They both either converge or diverge. So we know that this converges because it's a geometric series with r equal to 5 over 6. And the absolute value is just 5 over 6 is less than 1. So then we get this guy converges by the limit comparison test. Okay, so on to the next one, E. We've got the sum n equals 1 to infinity of n over n plus 1 times a half to the power of n. Okay? So as n goes to infinity, if we look at this piece, n over n plus 1, we see that that's going to approach 1. So its behavior is not going to affect what's happening in the limit. It's the 1/2 to the n. So you can actually either use direct comparison test or limit comparison. I'm going to use direct comparison, where I'm just going to say n over n plus 1 is just always less than 1 for any positive n. Okay? So then I know that n over n plus 1 times a half to the n is less than a half to the n. Okay? So if I look at n equals 1 to infinity of a half to the n, this is a geometric series with r equals to a half, less than 1. So we know it converges. So then, by direct comparison test, sum n equals 1 to infinity of n over n plus 1 times a half to the n converges. Okay, so just to summarize, we found that this guy converges. We found that this guy converges. This guy diverges, which was the one we were looking for. This one converges. And this one converges. So the answer would be C.